Okay, so we are going to be talking about the 555 timer, and the items that I want to discuss are in a particular order. Hopefully, if we go through this order, at the end, we have a very good understanding of the 555 timer chip and its working. So let's start with talking about the charging and discharging of a capacitor. And we've been seeing a capacitor from almost the first or the second week of classes, but we have not actually gone and looked at the transient analysis for a capacitor. We have always assumed that the capacitor is in steady state, but what happens when you charge it or discharge it? We have not seen that. So let's try to address that first. Then the second item on this list is talk about the internal circuitry of the 555 timer chip, and we will tie everything together by discussing the external connections. So what is inside the chip and what do you connect outside the chip? Before we even get into the charging and discharging, first we need to establish motivation. So what can be a purpose of using this IC? So it's an 8-pin IC which looks very similar to your op amp. So in terms of number of chips and the size, it looks very much like the UA741. It's again an 8-pin IC, but of course the pin outs are different and we are using it for a completely different purpose. So what is that purpose? Well, we can talk about the purpose by discussing the two configurations it usually appears in. So the first configuration that we are going to talk about in experiment 7 is actually a astable configuration or astable mode. And the other one that we are going to explore in EI in project 3 is the monostable mode. So in the astable mode, we could use this 555 timer to generate a square wave. So generate square wave, and that is going to be a free running square wave. And I could use such a waveform to trigger other circuitry to establish timing and synchronization in several modules that I may have in my design. So it's a very useful signal. And in fact, even humans have it, right? So, the thing that keeps track of time, every human has it, is the heart because it does the pumping at the regular intervals. So as a timing signal like this is essential, is fundamental to a lot of a design, circuit design. So that's what we can do with the astable mode. We are going to explore, as I said, astable mode in experiment 7, and we'll talk about the monostable mode in project 3. And with the monostable mode, you do not generate a square wave that goes on forever. Instead, you just generate one clean pulse, and you are able to control for how long that pulse lasts for by designing an appropriate circuit that has the monostable configuration. And we'll talk more about that in project 3. But that is going to be one pulse. And in the astable mode, it's going to be continuous pulses. And we are going to be focusing on the astable mode today. So that's as far as purpose is concerned. As you can see, it's very useful, very crucial, and this sort of a signal, you can control the on time and you can control the off time, which means that you have the control over the frequency and the duty cycle of such a square wave. So we'll see how all of that is being controlled by the design choices that we can make. Okay, so so we talked about the purpose, and something that is very crucial in the 555 timer is a capacitor. So that's probably one of the most important component in that discussion. So we'll talk about how a capacitor charges and discharges. So let's go up one and up one more and talk about the charge cycle. So what I'm doing over here is I'm connecting a DC voltage source to a resistor and a capacitor that are in series, and I'm monitoring the voltage across the capacitor. I'm calling the input voltage V in, and I'm calling the output voltage, which is essentially the voltage across the capacitor, as V out. I have the value R and C denoting the value in ohm and farad respectively, and I've connected ground over here. I'm using a switch that is open before time 0, and at time 0 I close the switch. The moment I close that switch, current is going to flow in this circuit, and it is going to charge the capacitor through this resistor R, because I've connected it to a voltage source. So if I connect it to a 5-volt source, for example, and I assume that initially, before the switch closes, the voltage across that capacitor is 0. So I'm saying V out of 0 minus. So at time 0 minus, just before 0, I'm assuming that it is 0 volts. So charge on the capacitor just before the switch closes is 0 volts. So the starting voltage is 0. Now, if I look at the current through a capacitor, we said current through a capacitor is related to the voltage across the capacitor by using a differential equation. I is C dV by dt. So if I were to apply a Kirchhoff voltage law to this loop, sum of voltages around the loop is 0, I would end up with a differential equation that I need to solve along with this particular initial condition. But I don't want to spend my time doing that complex analysis, which is part of a very involved or complex discussion meant for electrical engineers. I'm going to assume that I formed that differential equation, I substituted the initial condition for the voltage of the capacitor, and I solved for V out as a function of time, and I will end up with this particular solution. V out, which is the voltage across the capacitor as a function of time, is equal to V in, which is the input voltage that I am providing, multiplied by 1 minus e to the negative t over tau. Let me move this away so that there's no confusion. So that is the crucial equation that dictates how a voltage of the capacitor rises during the charging cycle. So it's essentially a barrel that is empty at the beginning, and you're trying to put charge to fill it up. And the claim is that it rises as a function of time based on this. Now, what is tau? Well, tau is called the time constant or the decay constant, time constant. And it depends on the value that you choose for R and C. It is essentially the product of those two, R times C. That's your time constant. And what is V in? That's the voltage source. And what is V out? That's the voltage across the capacitor that changes with time. So just to get a quick look at how it looks like, let's have a sketch. I have time on the x-axis. I have V out on the y-axis. And let us assume in red that my V in is, well, let's say I have this guy going up over here and there, and 0 until there. And I'll assume that this is some time t0, this is 0, for example. So I'm going to look at this, and based on this equation at the top, I'm going to try to sketch what the output should look like in, say, blue. So the output until t0 is going to remain 0, because I'm not closing the switch. That means that I'm not increasing the charge on the capacitor. This, by the way, is V in. So what is going to happen at t0, the time at which we start charging? Well, we claimed that that is going to be the equation at which it charges, so it's going to exponentially rise and eventually become the full charged voltage Vin. So that equation is essentially derived right there. That is the charge cycle, and it looks like that exponential charging. So that's as far as charging is concerned. So this is only for charge cycle. Next, using this particular equation, I can answer a question like this. How long does it take for a capacitor to charge from one voltage to another voltage? And the initial voltage, I am assuming that it is some supply voltage called VCC divided by 3, and the final voltage on that capacitor during the charging is 2/3 of that supply voltage VCC. Now later on today uh, you will see the reason why I have chosen those specific voltages, 1/3 supply voltage and 2/3 supply voltage. It will become clear in a few minutes. But I can essentially view this as, if a charge capacitor is charging, it is doing that. I want to find out if this is 1/3 VCC and that is say 2/3 VCC, how much time is it going to take for that to charge up? So I'm interested in how much time does it take to go from that value to that value. Well, I already know that from the previous discussion, I know that V out, which is the voltage across that capacitor, is V in times 1 minus e to the negative t over tau. What is V out? What is V in? V in is my supply voltage to which it that levels off. So that's the final voltage, as you can see over here. That's the final voltage. So that's going to be 2/3 VCC. V out is the initial voltage here, times 1 minus e to the negative t. Tau is simply RC. So if we solve this for t, you should get t should equal natural log of 2 multiplied by RC, which is essentially 0.693 RC. Note over here, R and C, those are the value of R and C, resistor and capacitor in ohm and farad respectively, that we have chosen to charge the capacitor through. We have chosen to charge the capacitor C through the resistor R. Alright, so that's an important result, and I'm just going to simply for now highlight this so that later on if I need to refer, this will be helpful. So time is, and that's for the charging cycle. Next, of course, if there is a charge, I can also remove the charge from that barrel. And I remove the charge by simply disconnecting that voltage supply V in. So if I remove that voltage source, now the capacitor can no longer retain that charge, and there is still a closed circuit. If I make sure that there is a closed circuit and there is still a resistor in that circuit, say I have a resistor, I have closed that circuit, and that capacitor has charged up, and now I have removed the voltage source. Now it has no choice but to discharge. So how does it discharge? Well, it is going to discharge by this equation. It's going to be a different equation. The voltage, say initially it is VO. That means that that's my uh, initial voltage. And VC as a function of time. So that's voltage across capacitor voltage. VO times e to the negative t divided by tau. Tau is again the same decay constant or time constant, which is RC, product of R and C. How does it look like? In this case, it is going to look like, so suppose I went up. So let's see. Let's do an interesting exercise here. This is T, this is voltage across the capacitor. In red, I will assume that it was 0 and it went there and it went there, and I removed that input voltage. In red, I have input. What is going to happen to the output, which means the capacitor voltage? 0 to begin with, it's going to start charging here, and then, well, let me charging, and then the moment I make the input voltage 0, the capacitor is going to discharge based on that equation right there. So it's going to do this, exponentially discharging based on that. So you had the charge cycle over here and you have the discharge cycle over here. Now using this, we can answer a similar question. How long does it take if the start voltage was 2/3 VCC? How much time does it take to go down to 1/3 VCC? Again, those choices will make sense later in the lecture today. But if I wanted to know how much time does it take for a capacitor to discharge from 2/3 VCC to 1/3 VCC, I can again use a similar process. So for voltage across the capacitor, I'm going to assume 1/3 VCC equals the initial voltage is 2/3 VCC e to the negative t over RC. I solve for t, it will come out to be exactly the same. Natural log of 2 multiplied by RC. Now, it's the same R and C. However, in the 555 timer, we can adjust different R's, so that we have different on time and off time, different charging time and discharging time. And we'll play that game later on. But I hope that you understand those two relationships and how they relate to the charging and discharging of the capacitor. Let's see. Having talked about that, next, let us talk about the internal circuitry of the 555. So for that, I'm going to look at page number 12 of the experiment 7 write-up. And there are essentially two figures on this particular sheet. There is figure D1, which is showing us all the external connections to the 555 timer. And there is figure D2, which shows what is inside that particular chip. So this is the internal circuitry, figure D2. We are going to talk about figure D-2 first, and then we will go and make sense of the figure D-1. So we'll do this in steps. And as you can see, we have two comparators, op-amp based comparators. We have seen them before in experiment 6. We have seen a transistor before in experiment 6. We have seen a JK flip-flop just last lecture. And we have definitely seen a voltage divider. That was class 1 of the semester. So there are several aspects of various elements that we have seen earlier in the semester, all put in one place with the 555. So let's start this with the simplest question. Where is the voltage divider? So if I look at this, I'm going to assume that this pin 8 of that chip, and we know that there are going to be 8 pins, I am looking at just that area. Perhaps I need to look at this. So hopefully this will slightly be better. Okay. So what I have here is pin number 8, to which I am supplying a VCC voltage. So this could be a 9-volt supply from the battery, or it could be the 5-volt supply from analog discovery. It could be any voltage that ranges between 5 to 15 volts. Any voltage. It's my choice. That's pin number 8. Pin number 8 is connected to a resistor, another resistor, and another resistor. The value of those three resistors are 5k ohm, 5k ohm, and 5k ohm. I hope now you see why the name 555 timer, because it is using three 5 kilo ohm resistors that are internal to that chip. So let's try to take a look at how this particular circuit looks like. So I'm going to analyze this in pieces. I'm going to only look at the piece that I have highlighted. So I have a voltage source that is connected to three resistors that are in series, and I have ground from pin 1 on the other end. This is VCC. So I've got R and R and R over here because of that R and that R and that R. And as you can see, I am interested in using P1 because it's an input to this op amp, and I'm interested in using P2 because it's a reference voltage to the second comparator op amp. So let me try to match them up. So this particular point is going to be P1, and this particular point over here is going to be P2 here. So let me just draw that there, and that is there. So what is the voltage at P1 going to be? Based on this, it's a simple voltage divider. We should be quickly able to compute the voltage across R, just one R, right? So voltage at P2 is going to be voltage across this particular resistor. So using voltage division, voltage at P2, I can just say P2. P2 should be, what is that? VCC multiplied by R divided by R plus R plus R. So 3R. What is that? 1/3 VCC. So that 1/3 VCC goes right there. Let me highlight that, VCC divided by 3 right there. Next, what is going to be P1? Based on voltage division, still VCC is the input voltage, but now for P1, I have two resistors that the voltage P1 is being measured across. So that's going to be 2R divided by 3R, which is going to VCC divided by 3. So 1/3 VCC and 2/3 VCC. Now I hope you have some understanding of why we chose those specific start and stop voltages in our earlier discussion of charging and discharging of the capacitor. That's exactly the reason why. Now that I have the voltage at P1, let me also highlight that over here. And in fact, I don't need this anymore. So 2/3 VCC divided by 3. I need to find a better spot. So P1 and P2 are 1/3 and 2/3 VCC. Those are our two reference voltages that are being used for comparison for the threshold comparator and trigger comparator. So two comparators that feed into a JK flip-flop. So let's see what is going to happen. So next we'll focus our attention on this particular comparator, threshold comparator. This guy has two inputs. Let's see. Come on. One of the inputs of the threshold comparator is P1, which is fixed. So that's 2/3 VCC. But the other input of the threshold comparator is actually a voltage that is in our control. Essentially, it is the external circuitry that controls that voltage, which is essentially the voltage at pin 6. So let me call voltage at pin 6 V6. V6 is being compared with 2/3 VCC, which is P1. So how can you have the comparison? Well, you can have two situations. This could be greater than this, or V6 could be less than 2/3 VCC. Two options. So V6 is greater than 2/3 VCC. What would happen? In that case, because the non-inverting terminal is greater than the inverting terminal input, my op amp is going to saturate high, whatever plus V is connected to. So that would mean that the output of the op amp is high, and consequently the input to the K is going to be 1 or high. So I can say K is 1 in that case. And if V6 is lower than 2/3 VCC, then the comparator will saturate low. I can write that as K as 0. Now similarly, I can write two more statements that correspond to the trigger comparator. In this case, my comparison voltage is VCC divided by 3, but the configurations are also reversed. So if I take a look at the trigger comparator, I'm using pin number 2 for that. So V2 is being compared with 1/3 VCC, two options. It could be greater, it could be less. So if it is greater, what would happen? Well, if the negative is greater, so sorry, if the positive is greater, we would get high. If the negative is greater, you would get low. So J would be low in that case. If the negative is lower, then you would get J as 1. So two statements that govern how that comparator or both of those comparators respond to whatever they observe on pin number voltage at pin 6 and pin 2, which are coming from outside the chip. Now those K and J inputs control the state of the flip-flop. And as you know, it can have four different possible states. You can have memory, you can have toggle, you can have set, and you can have reset. So set is the same as your jump, and reset is the same as your kill state. So now let's move on to one step ahead. What is going to happen, say if you have a situation where this is 0 and that is 1. Very possible. When is this going to be possible? It is going to be possible if V6 is greater than 2/3 VCC, and V2 is let's say greater than 1/3 VCC. So if V2 is greater than 1/3 VCC and V6 is greater than 2/3 VCC, K is going to be 1 and J is going to be 0. The moment these two are 0 and 1 respectively, and this particular flip-flop sees an active edge of a clock input, which is not shown explicitly over here. It is understood that it is there, it is clocking the flip-flop, but it's not explicitly shown here. What is going to happen to the output? Well, the output is going to get killed. So this becomes a 0, and then that becomes a 1. The moment you have 1 over there, you see what happens. It turns on the transistor over here. And the moment this transistor turns on, what is going to happen? The pin number 7, whatever you have connected to pin number 7, is going to discharge to ground. So whatever you have connected to pin number 7 is essentially now connected to ground directly, because you have your transistor being on. So I hope you see that. Let me highlight this in a slightly better way, and that's the discharge, pin number 7. Now that's one scenario. The other scenario is, let me erase this, let me erase that, that, and that. What is going to happen? If J input is 1, K input is 0. When is that possible? That is possible when my V2 is less than 1/3 VCC and V6 is less than 2/3 VCC. So if they are both less than their reference voltages. What is going to happen then? Well, we are going to jump the output. Jump the output means this goes to 1, that goes to 0. If that goes to 0, the transistor is off, which means pin number 7 is not connected to ground in this case. So no discharge possible. That's as far as the discussion about the internals of the 555 are concerned. Now we will apply uh, all these steps of analysis to the external circuitry of the 555 timer. Give me one moment. All right, so let's see how is it going to work. So let's say we have let me zoom in here. I have VCC, and as I said, it can be any voltage from 5 to 15 volts. I have connected pin number 8 to that and also pin number 4 to that so that there is no reset possible. I have connected pin number 1 to ground. I have connected that control voltage that I'm not using while I am in the 555 A-stable mode. I've connected it to ground using a 0.01 microfarad capacitor. But now I have three component values that are very crucial to this design: R1, R2, and C1. So what is going to happen initially? Let's say I have zero voltage across the capacitor C1, and if I have zero voltage across C1, notice what you did here. We connected pin number 6 and pin number 2 together. So whatever we had earlier, if I scroll down here, this threshold pin and the trigger pin, externally they are connected together, and they are connected to the capacitor C1. So I can say pin 6, voltage at pin 6 equals voltage at pin 2, which equals voltage across the capacitor C1, voltage across C1. So whatever voltage you have that is input to the threshold comparator as well as the trigger comparator, the input that is changing with respect to time is the voltage across the capacitor C1. The other input to those capacitors, as we have established, is fixed, 2/3 VCC and 1/3 VCC. Next, what is going to happen when we start things off, when we switch on the supply? Well, when you switch on the supply, pin 7 is going to be a dangling wire, which means that this is not going to be connected to ground. Pin 7 is not connected to ground because of the internals of the 555. Because remember, we said if the voltage across the capacitor or the two inputs is too low, lower than both thresholds, pin 7 is not connected to ground, so no discharge. So this is out of the picture. This is there, which is effectively going as the input. So your circuit looks like this. You have VCC, you have R1, you have R2, and you have C1. This is VCC, this is R1, this is R2, and this is C1. So how is the voltage across that capacitor, which is what we are interested in, going to change? Well, as you might imagine, the time constant over here for the charging of the capacitor is going to be R1 plus R2 because they are in series times C1. We said time constant or the decay constant is a product of R and C. Right now our R is two resistors in series and C is C1. So that's R1 plus R2 times C. So initially it is going to start at 0 and it is going to keep raising, charging. Until what time does it charge? It charges from 0 to a maximum of 2/3 VCC because the internal circuitry allows you to charge up to 2/3 VCC. The moment you reach 2/3 VCC and go a little bit above, K will be set to 1, J will be set to 0, which means that the transistor will become on and you will start discharging. So it can reach only to a maximum of 2/3 VCC. At that time, you will start discharging. Why? Because pin 7 now will be connected to ground internally. So you are going to discharge that capacitor. Goes down until you hit 1/3 VCC. And then again, you will charge up and go down and charge up and go up. So now you're going to start at 0, but after that, you will be going between 2/3 VCC, 1/3 VCC, 2/3 VCC, 1/3 VCC exponentially, which looks like that. And this process will keep continuing as long as your VCC is on. So during discharge cycle, the time constant is going to be slightly different. Why is that? If you look at this, the capacitor C1 charges through R1 and R2. However, if you look at the discharge cycle, because we have connected pin number 7 to ground, capacitor C1 only discharges through R2. So during discharge, your time constant is going to be R2 C1. So you have different resistors or different time constants dictating the on time and the off time. So as you can see here, we answered these two questions at the beginning of the lecture. How much time does it take for a capacitor to charge from 1/3 VCC to 2/3 VCC? We have proved this before. 0.693 times RC. In this case, during charging, you have R1 plus R2 times C1. For discharging, you have 0.693 times R2 times C1. So that's your on time and off time, T1 and T2. And this is of pin 3. Where is pin 3? Pin 3 is essentially the output Q. Right? So as you are doing that comparison, J and K will make Q either a 0 or a 1. And that being 0 or a 1 will make the output look like a square wave. So that's perhaps a very detailed discussion on the 555 timer. Now, I want to talk about a few parameters uh, that are a result of this. So in your design, what goes in your design? Well, we said T1 is your on time, which is what? 0.693 times R1 plus R2 times C1. Then T2, which we called it the off time, is 0.693 or natural log of 2 times R2 times C1. What is the period going to be? It's going to be T1 plus T2. What is frequency of this going to be? 1 over T. What is the duty cycle as a percentage? Duty cycle is defined as what? Percentage of the time period for which uh, square wave is on. So this is essentially T1, which is the on time, divided by the total time, T1 plus T2, as expressed as 100%. And if you put these equations in that, you will get R1 plus R2 divided by R1 plus 2R2 as a percentage. So duty cycle does not depend on the value of the capacitor C1, it only depends on the values of R1 and R2. Now a very interesting point that actually Derek just made is the fact that you cannot get less than 50% duty cycle with such an equation, because the lowest value of R1 can be 0. It will never be 0, but it'll only be greater than 0. The same thing applies for R2. It can only be greater than 0, which means that you can never get, no matter what you do with R1 and R2, you can never get less than 50% duty cycle. So what do we do? Well, let us suppose you wanted 20% duty cycle. If you desire 20%, then you generate 80% and use inverter. to get 20%. So, you can use a trick to get the duty cycles that are between 0 and 50%. Greater than 50%, you just get your R1 and R2 and C1, play along with those parameters to get those numbers. But by using an inverter on a NOT gate, you can flip the square wave and then get to a 20% signal. Okay, so let's see. We talked about frequency, duty cycle, on time, off time. Okay. Um, I guess, well, let's do one more. Um, I guess we can stop over here. All right, so let's stop over here and then I'll take questions.